Hello again. This is another video on trigonometry. We're going to talk about graphing trigonometric functions, sine and cosine, and the other four. Okay, so in the textbook, OpenStax textbook, this is chapter 6. Okay, I hope you're doing well. So let us get started and talk about that. All right, so we see that this chapter is all about graphing sine and cosine and other trig functions, right? And then we're going to also talk about the inverse trig functions. And we talked about trigonometric functions as tools we use to represent patterns in nature. Many things are periodic in nature. For example, the motion of the sun, the seasons, right? The movement of the planets. There are many situations where trigonometry can help us model the situation. So let's start with graphs of sine and cosine. Now, there are two different setup here. There is we talked about the unit circle, right? And we said that if the radius is 1, right, then the angle that we make here, whatever the angle is the same as the arc length. So arc length is the angle. And since we use, let me go back to this white area so I don't get that thing on my way. So what we have is unit circle, and then when we make an angle on unit circle, the arc length is the angle. So we're going to represent it with a real number t in radian, right? So you think about a number line, right, wrapped around the circle on both directions, in both directions. So there is a number line here actually. So there's like a 1 here, and then 2, and then maybe 3, and then 4, and so forth, right? 5, and 6, and 0.28. So we can think of a function of t maybe, and call it, let's say, sine t, and think of another function, g of t, and think of that as cosine t. And now a point on this circle has two coordinates, cosine t and sine t. As we go around the circle, the cosine, which is this distance, changes, right? If I go to another angle, the cosine changes to that much. If I come over here, if I come on this side, well, cosine changes to that much, right? So if we keep track of values of cosine, we have a cosine function. Now, one thing we can do is to open this number line that is around the circle here and put it in the coordinate plane. So that would be, instead of x coordinate, we call it t coordinates, t axis. So, and the y, we're going to call it g of t, or in this case, g of t would be the x coordinate of this point that goes around, right? So for example, cosine right here, we know is 1. So at 0, cosine is 1. So we go right there. And then as we go around, cosine, let's say at 45 degrees, is like a square root of 2 over 2, which is about 0.7. So at 0 is 1, and at maybe we divide 2 pi into 4 parts, and this is like pi over 2 here, and this is pi, and this is 3 pi over 2, and this is 2 pi. So between 0 and pi over 2 is pi over 4, so cosine is about 0.7. If this is 1, 0.7 is about maybe over here. And then when we go to pi over 2 here, cosine is 0, right? So it looks like cosine is going to go like that. And then at maybe pi, let's go all the way to pi right here. Cosine is -1. So -1 is about maybe here. Right, so it goes to -1. And then at 3 pi over 2 over here, right, cosine is 0 again. So it goes to 0. And at 2 pi over here, back to 1. Back to 1. So you see this graph right here is the graph of the cosine function, and that's the graph of one cycle, graph of one time going around the circle, the unit circle. Now if we do it again, well, we get the same graph, another cycle of it. Now if we go the other direction, then we get this graph, this cycle, and so forth. So if you start at t equal to 0, then that's what you're going to get. Now, since we like x to be on the horizontal axis normally, so what we can do, we can forget about cosine here being the x coordinate here. This x coordinate and the number x, the variable x we use here, are two different things, right? Here x is going to be the input of cosine, which is actually t. And here the x coordinate on the unit circle is actually what? Is actually the y coordinate here, right? So don't confuse that when we use x on the horizontal. That is just because we don't really talk about this x anymore. We're going to consider that to be what? The y over here. So as this goes around, we can call the input, instead of t, we can call it just x. So you can make this g of x equals to cosine x and graph it. Now we can do the same thing for the y coordinate, right? So let's see what happens if we do that to y coordinate. There you go, that's easy. So if you have a unit circle, we go around one time. Right here, what's the sign at 0? Well, let's graph it here. So again, we're going to assume t and then change it to x. So t is the angle we make here. And then the y coordinate is actually the sine of the angle. See, at different values, the sine would be this distance. So if we are over here, the sine would be this distance here, right? So it goes between -1 and 1, right there. It fluctuates between -1 and 1 as we go around. So we want to take this fluctuation and put it on this graph right here. So at 0, sine is 0, right? At, let's say, we divide 2 pi again into 4 parts, right? So that's pi over 2 pi and 3 pi over 2 and 2 pi. So at 0 is 0. Let's say in the middle here at pi over 4 we know is the square root of 2 over 2, which is about 0.7. So let's say this is 1, so 0.7 is about maybe here somewhere. And at pi over 2, sine is 1, right? So it looks like it's not a straight line. If you graph more points, you see it's not a straight line. It's actually a curve. And at pi is going to go back to 0. Sine of pi is 0. At 3 pi over 2 is going to be -1. So it's going to be right here somewhere, right? So it goes to 0 and goes to -1. And back to what? Back to 0 at 2 pi. So that's one cycle of sine. If we keep going, then we get another cycle and another cycle. If we go the other way, then we get this cycle, right? So that is the graph of f of t equals to sine t. Just like we did with cosine, we can just assume this t is x, which is the input, right? And as we go around, we represent the x, the angle or the real number, by x. And the y coordinate here is actually the value of the sine at any given value of t or x, right? Same thing. Okay, so that's the main idea we're going to work with in this chapter, and we're going to apply this to all 6 trigonometric functions. Okay, so this is what it is here, and I am going to actually animate this to show you what I mean. So let me animate this right here, this graph. So what we have here is, let me wait for it to download completely. Here we go. So what I'm going to do, I'm going to go to angle 0 right about, well, right about here. And then I want to zoom out so I can see at least 2 pi right here. That's good enough. All right, let me make it a little bit bigger. So there we go. So now I'm going to graph f of x equals to sine x. As I said before, I'm going to make the x-axis to be the angle or the real number input of sine, and the y-axis is the value of sine. Obviously, the domain is all real numbers because we can go around and make any real number this way or the other way, right? So the range here of this function really is between -1 and 1, because sine basically is stuck in this a little segment here between -1 and 1. So now I'm going to slowly, by 1 degree, move around. See, I'm increasing what? Increasing the angle. And notice that red circle on the unit circle, that is on the unit circle, and the blue one is actually on the coordinate plane that we want to graph. So really, we don't really need that unit circle here, the red one. So don't think of the x coordinate of the unit circle as to be cosine. Here, I'm imposing the red graph on the top of the graph, the blue one that we want to graph, right? So the red one is just a typical unit circle. Think of it as it's being over there on the other side, and is inside a different coordinate plane, right? But I put it here so you see the connection between them. So as I move the red one on the unit circle right now, is I'm going to be right at pi over 2, 90 degrees. So sine at this point is, see this right here, this number on the x-axis is pi over 2 in radian. And pi is 3.14, so 3.14 divided by 2 is about 1.6 something. I mean, 1.4 something, 1.3 something. Okay, 1.5 plus 1.6, let's say. It's about right there. And the y coordinate of it is 1. Now, as I move around, you see the red one, you go to pi, which is 180 degrees, right about there. You see sine is right here. So this number is 3.14 pi, and the y value is the value of sine, which is 0. And we can continue in one direction, in counterclockwise. We go 3 pi over 2, which is 270, and you see the value of sine is -1. See? And we go to 2 pi right there. And that's one complete cycle, 360 degrees. Now, if I go the other way, notice I'm going to turn around. Now, is going over that blue graph. That's why you don't see anything. But then I'm going to go back to 0 and go the other direction, the negative direction. And as you see, another cycle of sine is graphing right there. And I can go all the way to -360 degrees, which is a little bit past that. But you see it, right? And that's it. And in the notes, of course, you can see, you can zoom in and out, and I have instructions. If you zoom in and out, you lose the blue one. and you have to recreate it. You see, if I move this quickly, it doesn't graph enough points, so you would see a solid line. But you can like move this around, and it creates those points for you. And if you connect them, you get 2 cycles of sine, right? Okay, so that's the idea. Make sense? All right. So let me get rid of that and go back to explaining what's going on here. Okay, so that's the idea of using the unit circle to graph a sine function, right? Do not confuse the two things we are using here. We are using unit circle. Think of this as being inside a different coordinate plane that just, you have the unit circle, and you're just using what? Using that angle, which is the arc length here, t. We're going to represent it by x, and take this x, put it right here on the horizontal axis. And then as we move this point around the circle here, this x, of course, changes. And we're going to make the y coordinate in this graph to be the value of sine, which in this case would be the y coordinate of this point going up and down, right? And here it goes up and down as you go around the circle. All right, you got to practice with this and get this into your head, kind of. So when you see it, a bunch of neurons would fire together and wire together. Remember, that's how you learn. So if you have a bunch of neurons in your head, fire together, next time somebody says, do you know how to graph the sine function? All of that will be kind of crystal clear in your head. You can imagine all this in your head. Connection between this point rotating and this point going up and down. This idea is really, really useful in engineering. Later you're going to learn about, transformations, and it's going to be very useful. In engineering, they talk about going from the domain of frequency to domain of time and things like that. All of that will be crystal clear if you learn these ideas, okay? All right, so let's continue with this. So that's the graph of one cycle of sine function. And here's a chart. You can make a chart and graph it, right? So this is 0, 0, and you can do pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and so forth to 2 pi. And in general, over negative infinity to infinity, you're going to get a periodic function goes up and down. The electricity that you use right now is an AC electricity, alternating current. We also have DC electricity, which the voltage stays the same, right? And that's like a battery. Coming from a battery, voltage is DC. Coming from the city is AC. And you can read the history of DC and AC and the competition between Tesla and Edison, and the fact that Edison was mainly a business person and Tesla was a scientist. So, Edison tried to impose his business ideas on science, and Tesla was against that. And the idea was that Edison was for DC electricity and Tesla was for AC electricity. Is ironic because now you have batteries in the car called Tesla. But there was actually a lot of conflict there between science and business. Obviously, in practice, science always wins because it's based on scientific facts. So Edison tried to electrocute monkeys in public and try to say that AC is a dangerous electricity, shouldn't be used, because he had invested a lot of money in DC. But of course, eventually AC won, because it's much easier to transfer AC from the power plant to consumers. But anyway, you can read about all that. But the point here is that AC that you're using, the alternating current electricity, looks like a sine function. And you can actually get an oscilloscope, which is a device. You got two wires. If you connect it to electricity, you can actually see sine function coming from the outlet. And you can actually measure these distances, and you can measure this distance. We're going to talk about that, the period. All right, so let's continue. So that's sine, okay? Now what about cosine? Well, cosine is the same thing. So you can actually animate the cosine here. I can animate in the notes. If you click on this, you can actually download this GeoGebra file. This is under my account, but you can download the file and use it with GeoGebra. And GeoGebra, of course, is a free program that you can download. It looks like this right here. Just go to geogebra.org and download it. It's free. Okay, so the same thing happens with cosine. So I'm going to zoom out so I can see -6 to 6, because I know that's 2 complete cycle, right? So here you go. That's good. And let me get this out of the way. So now I'm going to go again to 0 here. And there. And clean this up. And start moving the point on the circle, as you see. And as I move around all the way to 360, you see that cosine is graphed. And cosine is really just like sine, except looks like we're starting at 0 at different place, right? So cosine, let me get this to show you. Let me get this, I can write on it. So you see right here, when you're over here on the unit circle, cosine starts from here, right? So if this is the unit circle, again, I said that you have to think about unit circle as somewhere else. I put it here in the same coordinate plane, but you should think of it that this circle is somewhere else. So when we are over here, the blue point is over here. When I'm over here, the blue point is cosine is 0. When I'm at pi, cosine is -1, as you see right here. When I'm over here, cosine goes back to 0. And when I go back to 2 pi, cosine goes back to 1. So it looks like one cycle of cosine looks like this. It starts from max and goes to some min, comes back to 0 and goes up there. So cosine looks like has one valley and 2 half kind of hills, right? And compare that with sine. One cycle of sine is one complete hill and one complete valley. Okay? Now, if you flip the sine and cosine over the x-axis, then you get 2 different patterns. You get this pattern, right? And for cosine, of course, you get this pattern, right? And we're going to talk about all this. But cosine function, now we know, cosine function looks like what? Looks like this, right? And you can have a table maybe and graph different points to see it. But again, this point comes from where we are on the unit circle over here. And this point is when we are over here. And this point is when we are at pi. And this point is when we are at 3 pi over 2. And this point is when we are on back to 0 or 2 pi, the same thing. And again, the domain of cosine is all real numbers, and the range is from -1 to 1, right? And that's what it looks like, from -infinity to infinity, cosine. So it looks like remember we have co-function identity, right? So it looks like cosine is basically sine function. So if you think about it, that is sine, right? But doesn't start from here, but starts from what? Right here. So if you think about sine function, right? If you take sine function and move it to the left about pi over 2, right? Then you get cosine function, right? See that? So all you have to do is move the sine function here to the left about how much? Pi over 2. And you get what? You get cosine function, right? So remember we said cosine also is related to sine. So two angles that end, if you add them, you get pi over 2, is pi over 2 minus x and x, right? So if you want to know what sine of x is related to cosine of pi over 2 minus x, or the other way around. But we're going to talk more about this. But for now, we have cosine and we have sine. One cycle of sine looks like this. And this distance here is 2 pi, and that's one period of the original sine function. And it goes from -1 to 1. And cosine, one cycle of it is half a hill here, one complete valley, another half here. And this number again is 2 pi, and distance here is 2 pi. So the period is 2 pi for cosine, and just like sine, it goes from -1 to 1, right? And there are some key points to graph sine and cosine. Is this one, this one, this one, this one, and this one. So there are 5 key points. If I know where those 5 key points are, I can easily graph sine. Same is true for cosine. There are 5 key points, and I need to graph them. All right, so now periodic functions. Remember at the end of chapter 5, we talked about periodic functions, and I said that we're going to talk more about this in chapter 6. So a periodic function is a function that repeats itself, and the smallest number that causes the function to repeat itself at that length, at that value, that number is called a period. So the smallest number that one complete cycle of cosine and sine repeat themselves is, of course, 2 pi. So if you take 2 pi, which is one period, and add multiples of 2 pi to a number, then cosine of that will be the same, right? Or sine, doesn't matter. So you see, here is cosine, graph looks like that. So if from here, if I make another cycle right there, so this value right here, 2 pi later, it repeats. Let's say this value here, right? 2 pi later, it repeats right here, right? So you pick any value, right? Let's say this value here. This value here repeats itself right there. How much later? 2 pi later. So every value will repeat itself 2 pi later. Now what about 4 pi later? This also works, right? So this value right here is going to be over here. It's going to be this value is going to be over here, I meant. So this is going to be over here. 2 pi later is going to be over here. 4 pi later is going to be over here. 6 pi later, and so forth. So if you add this many 2 pi's, and k is an integer, then you get the same value. This is also true if you go the other way. If you subtract, so if you make k -1, -2, -3, you get the same thing. So this value repeats itself, or you can say this value used to be 2 pi before, used to be the same as what it is now. in the past, okay, if you think of this as time. All right, so that's the idea of periodic. So sine and cosine are periodic. The period of sine is 2 pi, the period of cosine is 2 pi. The domain is all real numbers for both, and the range is -1 to 1, including -1 and 1 for both functions, right? Everybody should be able to graph one cycle of sine and cosine. Okay, so these are characteristics of sine and cosine. They are periodic with period 2 pi. The domain for both is that. The graph for sine is symmetric about the origin. You see, every point here has a friend on the other side, the same distance from the origin. Every point, right? This point right here has a friend on the other side, same distance, right? On the other side of the origin. So sine function is an odd function. Cosine function is an even function because it's symmetric with respect to y-axis. See, every point has a friend on the other side. If you draw a perpendicular to the y-axis and go to the other side the same distance, you find a point on the graph. And for every point that is true, so we say that cosine is an even function and sine is an odd function, right? So cosine is symmetric with respect to y-axis and sine is symmetric with respect to the origin, right? Symmetry with respect to the point is that if there's a point here, you want to find a symmetric point with respect to that point, you connect to that point and on the same direction, you go to the other side of the point, and these 2 points are symmetric with respect to this point. Symmetry with respect to a line would be if you have a point here, you draw a perpendicular to it, and then go in the same direction, the same distance on the other side. These 2 points are symmetric with respect to this line. And our line here is a y-axis, right? So all the points on the cosine axis, you can pair them into pairs of what? Symmetric points with respect to y-axis. All right. Now, of course, that's just the original sine and cosine function. Just like you know in algebra, if we have x squared function, right? If we have f of x equals to x squared, let's write it here. I can make another function, g of x, and maybe multiply x squared by some number, and then subtract x, some number from x, and then add some number. So this function is nothing but transformations of that function, right? Now, what are the transformations? Well, for every point on this graph, right? So let's say we have a point A and f of A on this graph. So this is A and this is f of A. Now the question is, what happens to the points on this graph under the transformation? Under the transformations, there are many of them here. Well, we divide the transformations into x transformations and the y transformations. What happens to the x coordinates of the points and what happens to the y coordinates of the points? If we know what happens to A and what happens to f of A, which is basically the y coordinate of each point, then we can easily see the new graph, right? And we can do that, of course, we did that in algebra, and we're going to do it with trigonometric functions too. In a moment, I'm going to animate this and show you what happens. But in general, if you have a new function and then multiply it by a bunch of numbers, let's say in algebra we said a f of maybe cx plus bx, plus c plus d, something like that. Here we use minus. I'll explain that in a second, but doesn't really matter. So if you have something like that, then what we are doing here is this. You have to think of this whole thing as the old y. So this is old y coordinate. And then a is the old x coordinate. What we want to know is what happens to a and f of a. So what happens to a and f of a? Well, that is going to turn into, now f of a, think of this f of something as f of a. So what happens to it? You multiply it by, well, I shouldn't have used a here. Maybe I could make it capital A so you don't confuse it with the other a. Okay, so you multiply it by capital A and add what? D to it. So we know what happens to f of a. You just multiply it by what? A f of a plus d, right? That's what happens to the y coordinates. Now what happens to the x coordinate? What happens to x coordinate is a little trickier because you have to reverse the operation, and also the inverse of it happens to the points. So if you multiply x by a number, you're in the equation, you're actually dividing the x coordinates by that number. So what we have to do, we have to set a equal to bx plus c. By a, I mean this a, the old x. And then solve for this x, which is the new x. So the new x, bx, is going to be a minus c. So the new x is going to be a minus c divided by b, right? So basically this new a here, new x, is going to be a minus c divided by b, right? So every point here now, we can transform it into a new point and graph the new function. Okay, again, this was just a review of what you know from algebra. I'm going to explain it a little bit more later. But let me animate this and show you what happens with the sine function when we change these values. So let it, I'm going to wait for it to load. Okay, still loading. All right, so let me make it a little bit. All right, so this is the regular sine function, because if capital A is 1, capital B is 1, C is 0, and D is 0, then we just get sine x, which you see right here. So I'm going to change this A. If I make this A bigger, what happens to the sine? It looks like it's a vertical stretch, right? So you see that number right here, right before sine, vertically it stretches sine, and you get those new heights. Now the question is, what does A do? Well, we say A vertically stretches sine function. Now if you make A something is smaller than 1, if it's smaller than 1, like 0.5, then it shrinks it. So it's a vertical compression. And if it's a negative number, then it flips it over the x-axis. So if you make the x value, the y values, negative y values, it flips them, you see? It's just like the x, the sine x function, but it's flipped over the x-axis. Okay, so that's what A does. So I'm going to put A back in 1, so we don't have any effect on it. If I can make it go back to 1. Here we go. So that's 1. All right. Now, what does D do? Well, D is a vertical shift, you see. just moves the graph up and down, you see? So that's what D does, very simple. So I'm just going to leave it at 0. What does B do right here when you multiply x by a number? Well, B is called the wave number. Whatever that number is number of cycles in one complete period of the original sign. So a complete period of the original sign is 2 pi. And 2 pi, remember, is 6.28. So notice right now we have one cycle in 6.28. And that is because B is 1. See that? Now, if I make B bigger, let's say I make it 2. Now, notice this is 6.28, right? So now in 2 pi, there are 2 cycles. 1, 2. 2 cycles up to 6.28. So this number determines how many cycles of sine we're going to have in 2 pi radian, right? And if it's, let's say, 1.5, then here is 6.25. Looks like 1 cycle and a half. That's 1.5. So that's called the wave number. Now, let me put it back to 2. So notice that if this number is 2, then the period is cut in half. So the period is given by 2 pi divided by this b. So in this case, the period is pi, you see. At 3.14 right here, we have what? We have 1 cycle already. So that's what B does. And C, you know, in algebra, you learn that if you subtract from x, you move to the right. If you add to x, you move to the left. Same thing is true here too, except you're not subtracting from x, you're subtracting from bx. So in order to understand what you're subtracting from x, you have to divide by b. And if you divide by b, you see you're subtracting c over b from x. So c over b is called the phase shift. So c basically is going to move, I made b 0, I have to make it 1. Here we go. So c, as I change it, notice what it does. It just moves the graph to the left and to the right. Doesn't change the shape of it. It just changes the graph, moves the graph to the left and to the right. How much does it move it to the left and to the right? Is c divided by b. In this case, b is 1. So in this case, it's just 1.31, as you see. So it moves it to the right and to the left, depending on whether it's positive or negative. Now remember, this number in the formula, we put a minus here, just by convention. So if c is negative, then since this is minus here, it makes it plus. So you go to the left. And if c is positive, you go to the right. That's why they put a minus here. So when the c is positive, we go to the right. And when the c is negative, we go to the left. It makes more sense intuitively. All right, so that's the idea, and that applies to cosine as well. So let's practice with this. So we're going to do it one at a time, one of these letters at a time. I did something. Here you go. So B. So capital B in the formula determines, remember we have sine bx minus c plus d, and then there is an a here, right? So this b right here, absolute value of b, we take absolute value of b. It could be negative, but usually we assume this is positive, because if it's negative, we can use identities to write it as something with a positive coefficient. So for now, let's say absolute value of b If you divide 2 pi by absolute value of b, you get period, always. Remember, b is a wave number, so if is that many cycles in 2 pi. So if you want to know what's the length of one cycle, from here to here, well, we take 2 pi and divide it by that number. Now, if that number is 1, then of course this distance is 2 pi. Now, if that number is 2, then that distance is going to be pi, right? All right, so and you see over here the effect of what b is. See this red one, b is 1. In this one right here, b is 2, so we get 2 cycles in 2 pi. And for this one, b is 1/2. So if you divide 2 pi by 1/2, you get 4 pi, right? So that means in 2 pi, only half of sine function happens. The other half is going to be way over there. So that's 4 pi. So you see now we have, this is like period is 4 pi for that one. See that? All right, so that's the idea of what b does, right? So if b is greater than 1, obviously the period is going to be decreasing. And if b is a fraction, then the period increases. Here are some examples. Determine the, should say the here, period of the function. So the number b actually has pi in it. That's okay. It's just divided by pi over 6. And 2 pi divided by pi over 6 is 2 pi times 6 over pi. The pi's go away, so we got 12. So that means the distance from here to here is 12 units. The period is 12 units. Okay? All right. Now, the example, determine the period here. Well, now the period, the b is 1/3. We divide 2 pi by 1/3, you get 6 pi. So again, the distance from here to here, one period, is 6 pi. Okay? Now, what about the a, number a? Remember, we have a sine bx plus, well, we use minus c plus d. So what does that do? Well, that's called the amplitude. Amplitude is the distance from the midline to the max and from the midline to the min. That distance is amplitude, and that is given by absolute value of this number. Remember, this number could be negative, and if it's negative, then the graph is flipped over the x-axis. But the absolute value of it is always the distance, basically, from the midline to the top of the hill or from the midline to the bottom of the valley, right? That's the amplitude. And notice here the amplitude here changes as a gets bigger and bigger, right? And that's what it does. And we saw it in that animation. You see amplitude here is 1, 2, 3, 4. So y equals to d, this number right here, is the midline. So the midline of one cycle is y equals to d. Now to graph these functions, we're going to graph one cycle in a rectangle. And a rectangle is going to have a midline, and the midline is always at y equals to d, including the sign here. If it's minus d, that would be minus d. And one cycle of sine looks like this, of course, right? So remember, there are 5 key points here. So the midline is y equals to d, and that is vertical shift, right? If d is 0, we start at 0. Now, how do we get that d? It looks like d is the maximum plus the minimum divided by 2, right? Always. So the formula for d is the max plus the min divided by 2. And we're going to talk about this in a second. But that's what this number does, is the amplitude. Absolute value of it is the amplitude. All right, what is the amplitude of the sinusoidal function? A sinusoidal function is a function that looks like, a sine bx minus c plus d, right? So what is the amplitude of the sinusoidal function given here? Well, is what? Absolute value of -4, which is 4. So to graph this, we're going to graph a rectangle, right? This rectangle here. Now, without the graph in it, of course, first we decide on where this rectangle is. How do we know where that is? Well, first thing we need to do is what is the midline? And the midline here is 0, because d is 0. And then we know that the max and the min happen at what? Happens at pi over 2 is min, because is what? Is negative. So remember the pattern for sine looks like this rectangle is divided into 4 parts this way. So there is a hill here and there is a valley here, right? And this number is y equals to d. So this distance here is absolute value of a, and this distance is absolute value of a. So the max happens at pi over 2, and the min happens at 3 pi over 2. But if this number is negative, then you have to flip it over the x-axis. Again, you divide into 4. And if that number is negative, the pattern would be this way. So now we have a valley here and we have a hill here. All right, that's what we have here. So the point here is to find the amplitude, and the amplitude is 4, right? So here we know from the midline we have to go 4 units down at pi over 2 to get the min, and from the midline at 3 pi over 2 we have to go up 4 units to get that. Once you have these 5 points, this one, that one, and that one, you can easily graph sine if you know the pattern. All right, so moving on. Notice that this function right here, c is not subtracted from x, it is subtracted from bx. So negative c is called the phase, but that is the number that you get if x is 0. So if x is 0, you get phase, which is negative c. But that's not what we are interested in. We are interested in phase shift. And that is how much the graph is moved to the left or right. The sign of this tells us whether it's moved to the left or moved to the right. So if the c over b is positive, then the graph moves to the right. And that's why we put a minus here, so that when the shift is positive, it goes to the right. Right? So really, c is this number after the minus. C doesn't include this minus. Minus is part of the formula. So I have to keep the minus here. So if you have, like, let's say I have 2x plus 3 here, I got to write this as 2x minus negative 3 to see what c is. C is negative 3, right? So don't get that confused. All right. So c over b is our phase shift. If it's positive, it's to the right. If it's negative, it's to the left. And is that much to the right or left? And when you factor b out, you see c over b. So from algebra, you know that if you subtract something from x, the graph moves that much to the right. If you add something to the x, the graph moves to the left that much. So if this value is negative and a negative becomes positive, so it moves to the left because you're adding to x. All right, so Now, find the phase shift, amplitude, and the period for this function. Now, right away, we know the amplitude is absolute value of 3. So amplitude is 3. The vertical shift is 5 units up. So that means y equals to 5 is our d, right? The midline, right? Now, right here, since 8 is outside of parentheses, if we write it this way, right, 8 times x minus negative 4, so this is our c, right? C is negative 4. So what is the phase shift? Where phase shift would be, the phase shift is going to be C divided by what? C divided by B. But in this case, if you factor the 8 out already, right, you already divided it. So really, if you write it as 8x plus 32, right, you see that? I did that on purpose so you don't get confused if you see it. See, if I give you this function this way, or if I give it to you this way, you should know that these are exactly the same, right? There. And also, we can write it this way. Or we can write it this way. Let me also write it here. See, all these 4 should not confuse you. You should understand that these are all the same, right? So according to our definition, the phase shift is C over B. Now in this case, this is not C, right? This is actually, we divide it to get it, right? So that is the phase shift actually, because we factor the 8 out. If you factor the 8 out, you actually get the phase shift here. But if you keep the 8 here, then you have to divide this, right? You have to divide this right here, which is C, by B. Only in this form, negative 32 is C and 8 is B directly. In any other form, you have to figure out what C is. C is not 32 positive. C is not positive 4. C is not negative 4, right? So you have to understand that that's just a matter of notation, which letter we use for what. So in this case, the phase shift is negative 4, and our C is actually negative 32, and our B is 8. Okay? All right. And the period, of course, is 2 pi divided by 8, so it's pi over 4. All right. So while C relates to the horizontal shift, D indicates the vertical shift from the midline, and we talked about that already. So basically moves the graph up and down, and I showed you in the animation already. Given a sinusoidal function in the form, this form, identify the midline, amplitude, period, and phase shift. So these you should be able to do right away. The reason we do that is because then we can decide exactly where this rectangle is, right? And what is the length of the rectangle here? And what number do we start with? And what is this number? And how much do you go up and how much do you go down? All of those are given by these 4 numbers here, right? The phase shift is the first number we start with, right? So that's that. And this number here is y equals to d, this line, the midline. And the distance over here is capital A, right? Absolute value of capital A. And these points right here, these points that we're going to have, depending on whether it's sine or cosine, if it's the regular sine is going to look like this, right? It's going to have a hill and a valley. If it's a regular cosine, it's going to look like this. It's going to have half a hill here, a valley, and a half a hill here. If it's flipped, if it's a sine that is cosine that is flipped, then it's going to start from here. I messed it there, messed up. Here you go. It looks like that. And if it's flipped sine, you know that it's going to look like this, right? So depending on what you have, and how do you know that? You look at the equation to figure out. First of all, is it cosine or sine, and also whether this number is negative or positive. If it's negative, it's the flipped one. If it's positive, we're talking about these two. So whichever you have, then you have to decide. You can easily find these points. Because you get this point, of course, this number here is C over B. The next number you get by dividing the period into 4 parts and keep adding that partition to get the rest of them. Once you have these x coordinates, then the y coordinates are easy. You get it from the pattern, which pattern we have. Okay, we need to practice with this, of course. So here you go. So this is determine the midline, amplitude, period, and phase shift of this, and then we can graph it. All right, so right away we know the amplitude is 3, right? And the D is 1. So we're going to create this rectangle. You see that yellow kind of rectangle right here? We know exactly what that is, right? We know the midline is y equals to 1, right? And so that's the midline of the rectangle. And we know that the period is 2 pi divided by 2, which is pi, right? So that means the distance from here to here is only pi units, right? Now, what shape do we have? Is a regular sine with a positive a. So it's going to look like, just a regular sine. It's going to have a hill here and a valley here. So the graph looks like this. But what these numbers are, we figure out, of course. We can figure them out. So we already know the middle line is y equals to 1, right? That's y equals to 1. And we know the length of it is pi units. So all we have to do is think of the original sine function, right? The original sine function. We have to transform these 5 points here. And we can do it 2 ways. We can actually specifically take each point and transform it. Or we can say, okay, this distance here is from 0 to 2 pi. What happens to that? And also this distance here is from -1 to 1. And what happens to that according to this transformation? Well, again, as I said, we can do it 2 different ways. If you think of transformations, this is goes to 0 to pi, obviously, because the period is what? The period is pi. And also, the c here is 0. So that means there is no what? There is no phase shift. That means we start with 0. Not on this one, but on the new one. So x value here is going to be 0, right? So we start the rectangle at 0, and we're going to end it at what? End it at pi, because the period is pi. You can just divide this into 4 parts and get these, right? Now, what happens to the y? Well, the y, is negative 1 to 1, and what transformations happens to, let me erase all that. So remember we talked about a and f of a. So think of this as f of x. So what happens to a point a and f of a? Well, a and f of a goes to the y-coordinate. Think of this as the old y-coordinate. So you multiply it by 3 and add 1. So you get 3f of a plus 1. And what happens to x? Well, to find the x, what you do, you take your old x and set it equal to whatever you have inside the parentheses here. And then solve for x. So x is 1/2 a. So this transformation is going to take all the x coordinates and cut them in half. And it's going to take all the y coordinates, multiply them by 3 and add 1 to it. So that means all the x coordinates, if you think of it this way, the x coordinate of the original rectangle of sine x, right, which were from 0 to 2 pi, now they're going to go from what? So what's 0 divided by 2? We have to multiply it by 1/2, right? So these are x coordinates. These are x values. So 0 divided by 2 is 0. 2 pi divided by 2 is pi. So 0 to 2 pi goes to 0 to pi. And what happens with these y values here? Well, remember, the y values are multiplied by 3 right here and add 1. So what's 3 times negative 1 plus 1 is negative 2. What's 3 times 1 plus 1? 4. So again, let me clear everything here. So we can easily see 2 different ways how to graph this one rectangle, right? We can take the original rectangle of sine after we realize this is just a regular sine, right? We get original rectangle that goes from 0 to 2 pi and goes from negative 1 to 1. We're going to take that and apply the transformations and get the new rectangle and then graph it, right? Or we can take the 5 numbers, 5 key points, and convert those 5 key points into the new 5 key points and just graph the cycle, right? And we're going to do it both ways. So let's, in this case, we got the period is pi, we got the midline, we got the amplitude, and there is no shift. So this is how we're going to try to graph this, right? So if we have a transformation of sine or cosine to graph, we're going to start with the original graph of one cycle of sine, whether it is regular sine or flipped sine, right? And then use transformations to see what happens to this rectangle and what happens to the 5 key points here, right? 5 key points. And once we figure that out, then we have a new graph and we are done. We don't have to graph the whole thing, we just want one cycle. So first we have to know where the rectangle is and then where the points go. How do you know that? How do you figure that out? Well, we're going to start with thinking of g of x to be sine x, because we usually use f of x for the new one, so I use g of x for sine. So g of x is sine, so we think of f of x as 4 times sine x. So this graph transforms the sine x. How? Well, for a and g of a, on sine, regular sine, right here, what happens to the y coordinate? You just multiply it by 4. This is old y, multiplied by 4. So GA and G of A is going to go to 4G of A. And what happens to x? Nothing, because there is no transformation on x, so x remains the same. So you can easily see where the rectangle goes, because this distance is what? Is from 0 to 2 pi. So from 0 to 2 pi, what happens to it? So 0 to 2 pi goes to 0 to 2 pi. Why? Because these are x values, and we just said x values don't change. So that distance is still from 0 to 2 pi. Now what happens with this distance here, which is from -1 to 1? Well, we have to multiply by 4, because these are what? Y values. So multiply by 4, you go to -4 to 4. So -4 to 4. So now you have a rectangle that goes from -4 to 4 on the y's and goes from 0 to 2 pi on the x. So you can easily graph this blue rectangle here. Now inside the rectangle, you just had a regular sign. You can just divide the rectangle into 4 parts and just graph it. Or you can specifically see where the points go. And that's not necessary in this case, because once you have the rectangle and you know the shape of it, you can divide the rectangle into 4 parts, right? And you know where the points are, right? So if they're from here to here is 0 to 2 pi, then the whole thing, you divide 2 pi by 4, you get pi over 2. What number do we start with? 0. So what's the next one? Pi over 2. What's the next one? So 0 plus pi over 2 is pi over 2. Pi over 2 plus pi over 2, pi. Pi plus pi over 2 is 3 pi over 2. 3 pi over 2 plus pi over 2 is 2 pi. I shouldn't put point here, I should put mark, right? So these are the x values of these key points. And since we know the shape of it, we know the values, the y values. All right, but you can use this transformation here and apply it to every point here, right? Apply it to every point and just transform them to these new points, right? This one, that one, that one, this one, and this one. All right, so I'm trying to make concepts clear so you can do it on your own. I don't want to take you through a bunch of nonsensical steps, and then you do 10,000 of them and you get used to it, and then in 10 minutes you forget it. So you got to understand why this method works and how. And once you understand that, you do it on your own easily. So we can do that. As I said, you can apply the transformation to every black point here and get the red points, right? So what are the key points? The key points are 0, right? The x values of key points are 0, pi over 2, pi, 3 pi over 2, 2 pi, right? And according to this transformation, nothing happens to them, right? They stay the same. And corresponding key y values are 0, 1, 0, -1, and 0. And what happens to them? We say that if you think of g of x to be sine x, that's the parent function. So a and g of a, under this transformation, transforms to a and 4g of a. So the x coordinates of these key points don't change, but the y coordinates are multiplied by 4. So here are the key points: 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, 2 pi 0. What happens to them? Well, the x values don't change, 0 pi over 2 pi, 3 pi over 2 pi. Y coordinates are multiplied by 4. Multiply by 4, multiply by 4, multiply by 4, multiply by 4. So these are our new points. We just put them there and we have a graph. Right? Notice that we didn't need the rectangles anymore in this method, because all you need is the points, and you have to know the shape of the graph. And you know the shape is a hill and a valley, and you have the graph. Okay? So let's look at another one. Here we go. So graph one full period and state the amplitude, period, and midline. So state the maximum and minimum. Now, what shape does this have? It looks like cosine flipped, right? So we know that this is going to look like what? Cosine function, but is flipped. So it's going to look like, make a mess here. Oh, what am I doing? Here we go. This thing is so slippery. There. So we know that the shape doesn't start from the top, but starts from the bottom, right? So it's going to start from here and go up there and go like this. So we know the shape is like this. So there are key points that we have to see where they are. But that's what it's going to look like, right? Because of that negative there. So, so how do we do that? Well, let's look at the transformation. Think of g of x to be cosine x, right? See? Now, what happens? Think of what happens to this whole thing as the old y. So the old y is going to get multiplied by -2, you see? So the old y, which is this one right here, is going to get multiplied by -2. Now, what happens to x? Well, to figure out what happens to x, we have to simplify inside the parentheses. If there are like two minuses, we can just write plus. And take this thing inside, this right here, and set it equal to the old x, which is that. And then solve for this x. And if we solve for x, we have to subtract pi over 6 from a and divide by pi over 3, as you see here. So the new x, you call that new x, is the old x minus pi over 6 and then divided by pi over 3. That's how you get the new x out of the old x. Once you know that, then you can easily graph this function. So let's graph it. So, we got I explain here again. So the rectangle, the original rectangle of cosine, which goes from where? From 0 to 2 pi. And then it's from -1 to 1. What happens to this rectangle? Where does it go? Well, the 2 to 2 pi, if we apply the transformations to these x values, right? So 0 minus pi over 6 divided by pi over 3. And then 2 pi minus pi over 6 divided by pi over 3. You can use a calculator to do that. You end up with -0.5 and 5.5. So that means we get a rectangle that the first number is -0.5 and the end of the rectangle is 5.5, right? Now, what happens with -1 to 1? Well, you just multiply by 2, so you go from -2 to 2. So you know exactly where this rectangle, this cycle of cosine is. And remember, we knew the shape of it, right? Doesn't start from here, but it starts from here and goes up, and that's it, right? That's where this cycle is. Now, of course, based on the x coordinates here, based on the y coordinates, -2, 2, you know the x-axis has to be in the middle here somewhere, right there. Now, since this is negative 0.5, the y-axis should be somewhere over here. And you see you have one cycle of this cosine. So it's going to look like this, right? And I graphed it here, one rectangle. You can put the x and the y-axis. Now, if you want to do it exactly using transformation of all the original points, you can think of original cosine, which is, original cosine is, starts from here and then goes there and then goes there. Original cosine, not flipped, right? Now, we know because this is negative, this is going to be flipped. But if you want to transform the points, you have to transform the original cosine, right? So these are 5 key points. You're going to take those and use the transformation that we just talked about, right, to transform the x and the y coordinates. So the points are these points. They're going to transform to these points, right? These 5 points. And you graph the new 5 points, you have a graph. You don't even need the rectangles. You just need one cycle. That's what one cycle is. And based on the x and the y values, you know where to put the x and the y axes, right? X-axis goes between max and min, and is right there, right? Because max and min are 2 and negative 2. So x-axis goes in the middle. Let's say the max was 4 and the min was 2. Then the x-axis, of course, will be over here, right? So you see, it's not that hard to graph these. You just have to use these methods. Either you transform the rectangle, figure out the shape of it, and just graph it. How do you figure out the shape? Either is regular cosine or flip cosine. Either is sine or flip sine. And you graph it. Once you have the rectangle and you know one cycle, you just graph one cycle inside. Or you could just graph using the 5 key points, using transformations. Move the 5 key points according to transformations, you have a new graph. All right, so again, here's another one, cosine 2x, using the same kind of idea here. We can find the amplitude, which is 1, right? If you compare it to that. See, amplitude is 1, b is 2, c is 0, d is 0. And again, you can easily figure this out, right? You know this is a regular cosine. So the shape of it is going to look like this. It's a regular cosine. You can either move the points or rectangle, right? In this case, I want to just move the rectangle. So the rectangle would be from -1 to 1, and this is from 2 to 2 pi. So what happens to it? Well, it looks like the transformation is what? The transformation is going to be g of 2x, right? So if you have a and g of a on cosine, what happens to it according to this transformation? Well, it looks like y doesn't change. Y remains the same because nothing happens to this whole thing, right? It's just by itself. And then the x coordinate, we let a be 2x, so the new x is 1/2 a, right? So 1/2 a. That's the transformation. So x values are going to get divided by 2, and the y values remain the same. So the new rectangle is still would be between -1 and 1, right? So this new rectangle is between -1 and 1. But the x coordinates, you divide by 2. 0 divided by 2 is 0, so still 0. 2 pi divided by 2 is pi, so that's pi. So once you know where the rectangle is and you know this is just a regular cosine that looks like this, so you just graph it right here. Or you can get these 5 points again and transform them according to this transformation right here and graph it, right? All right. Now, max and min. Now, based on the shape of regular cosine, you know there is a max here and there is a min here in the middle. And there is another max here, up here, right? So between 0 and 2 pi, the maximum is 1 that occurs at 0, right? And again occurs at pi again, right? And the minimum is -1, and it occurs right in the middle of 0 and pi, right here. Based on the shape, you know that. Okay. And so here is another one. Again, to graph this, we can use either method. First of all, we know this is regular sine. Y is not flipped, right? So we end up with a regular shape of the sine function, which is what? Which is one hill and one valley. So it's going to look like that. It's going to look like that. One hill and one valley inside a rectangle. What rectangle? Well, we can decide on where this rectangle go. Remember, originally it's from -1 to 1 and from 0 to 2 pi. Where does it go? Well, what are the transformations? Well, again, we're going to write it this way to figure out what the transformations are, right? So you see right here, let g of x be sine of x. So think of this as f of g of 8x plus 32 plus 5. If you multiply, is 8x plus 32, right? So the y is going to change according to this transformation. Multiply by 3 and add 5. That's what happens to the y coordinate, right? So this is the y coordinate. And what happens to the x coordinate? Well, we're going to take 8x plus 32 and set it equal to a and solve for x. So x is going to be a minus 3 divided by 8, right? So a point here, a and g of a, is going to go to a point a minus 3 over 8 and 3g of a plus 5, right? That's how we can transform the points or just the rectangle. So we can apply this to 0 and 2 pi and apply this to -1 and 1 and find a new rectangle. Okay, so 0 to 2 pi, if you apply these transformations, ends up being that, goes to -4 and pi over 4 minus 4. So this is -4 on the x-axis. And then this one, this number on the x-axis is going to be pi over 4 minus 4, whatever that is. It's like -3 something, whatever it is. That's what it is. And what happens to the y, -1 to 1? Well, it goes to 2 to 8. So this number right here is 2, and that number right there is 8. So you see this rectangle is going to go to from 2 to 8, and on the x-axis is from -4 to pi over 4 minus 4. Okay. All right. So so finding the vertical component of circular motion, I'm going to add this to the next video. Okay. I'm going to stop this video here and continue with application on the next video. So again, let me go back here and say bye to you. I see you in the next video.